So all right, thanks for being here. This is about LMFIT. It's a minimization library. So I assume you have IPython notebook, but if you don't have, I think you can even do it through Python. And I assume you have installed the library itself. Are we good with that? Okay. So all of us have been in a situation where we want to solve an optimization problem. And what it means usually is to minimize a function, or let's say, which is the case when you want to fit a model to a bunch of data sets. So you have some data points. You don't need to have this. I'm just showing it for us. And we know what it is, but for the purpose of the tutorial. So we have some data points usually, and we have a model, and this model has some parameters, and we want to fit the parameters to this model to these data points. And what it really means is that you really want to minimize this chi-squared function. So, every software or program you work with has some kind of packages to do that. And Python itself has a conventional, like a standard package to do that. But this LMFIT package is, as we're going to see, is going to give us some extra benefits and flexibility and advantages, as we're going to go through not every, but some examples. But if you really want to see what's going on with this package, you have to see the website. And it has a complete description of what is in here. So I decided to start with a very simple example. And we can just go through the whole process here. So let's start with just importing the things we want. So let's just import numpy as np. And because we don't have to, but we can also plot things, so we can just import that. Import matplotlib, pyplot as plt. And if we want to have everything inside our notebook, we can use this magic command, as you know, matplotlib inline, or matplotlib inline, where all the plots we have would show up in this page. Okay. So let's just go with this simple example. Imagine I have some data points. I just go with a very simple case where I have 0, 1, say 2, and 3 as the x component of my data point.
I'm assuming you're printing plots just so they're floats.
Yeah, but we don't have to, but yes. So the data points, like the y point, would be some numbers. I chose some numbers so that it more or less fits to a quadratic function for our purpose. So just to be on the same page, we can have the same numbers. Let's say these are our data points, like 5, 10.7. So you can already guess that a quadratic function can fit to this, more or less. But we can also plot it just to see for future use. So let's just plot x and data. And we have our data point here. Now let's just fit an x squared function to that. Not fit, just plot an x squared function on top of that. So we can say we have an x array, which is from -1, let's say, to 4, with some spacing. And then range Okay. X array is numpy arrange. Okay. And let's plot that. X array, we're going to plot this vector, and the function we want to plot would be this X array squared. Okay, and we can go with a red curve so that we can see. Okay. So obviously it's not the best fit to this data because I just shifted everything, all the data points by 1, right? So if I copy this guy and I just add an offset to that, let's go with green, then it's a better fit. It's not a perfect fit because there is random fluctuations, but it's just a better fit. So we're good?
This is not the optimal solution.
No, it's not. We're going to get there. I just wanted to start like manually fitting and then just...
optimizes
It's quite the package.
Yeah, it's the package actually. I do it by hand. Now, okay, next step actually would be that let's define a function which does that for us. So we're good now. Let's define the function called getResidual, and this is the one we're gonna like optimize or minimize. So we can define that, and this function is gonna get a dictionary of what is called vars, which is just a dictionary of parameters we're gonna define in a second. It's gonna get some x data point and some actual data point. We know we want to fit a quadratic function. So let's say I say A is this dictionary vars the zeros component, and say B is vars first component. And of course, we have to define that. But our model is the residual between the data and sorry, our model would be a quadratic function, which is like x squared with this amplitude A plus the offset B. And what we want to return is what we have from data minus the model. So it's going to be the residual between data and the model. Now, so we want to make sure our thing is correct, our function is defined properly. Now let's define some variables. So vars could be, say, 1 and 0. Like the amplitude would be 1, the offset would be 0, and we want to make sure our function works. So we say print function for the variables I have and the x and y of my data. Okay. So the only thing is that I defined my x was a vector with 4 elements. So I'm going to get 4 residuals from this model. For each x, I'm going to get a data minus model, and my x is defined here, as you know, and for each of them, I get a residual. Okay. So
here, vars is only containing parameters and ingredients.
Yes,
Okay.
we defined it like that, but it's like an intrinsic function which keeps a dictionary of variables. Now, what we want eventually would be this chi-squared, or this difference, which is the data minus model. So it means that what our model, what our function is calculating is just this guy. So we have to square everything and then sum over. So let's just do that. It is going to be our chi-square. So what I'm going to do is print sum of output of my function. Residual of vars x and data. Yeah. So this is practically the chi-squared we just defined, like saw up there. So with this fit, with these values of vars, I have this chi-squared. And this is the one we want to minimize.
Wait, is the data squared? You probably have to square it, right?
Oh, yes. Great. Sum of this guy square, right? So we can just test that if I change, I know that I have to have an offset of 1. I know it's from here. Okay, so I can just see how if I can already get a better fit.
I don't think you're squared. Square to go one farther out, right?
Yeah.
So you want to square each.
Just the difference before the sum.
Yeah.
And with non-primers, I think it gets applied to each element here.
Yeah. So let's just see how that works. If I define my vars to be 1 and 1, and if I say just print the chi-squared thing, in sum of get residual of vars and x and data squared, I should expect to get something smaller, right? Some smaller value. Now let's see if that works. So it works. It's a better chi-square. So we already manually had a fit. Okay? So all we want to do now is that these packages do this for me rather than us just doing trying every combination. Okay? So as I said, so are we good? Any questions? We're good? So Python has a built-in function. It's called, it's in SciPy, and it's a least squared function. So let's try that. What we need to do is to import this library from SciPy optimize. We're going to import least squared. Okay. And so this function is this library is gonna take a function and some variables and some arguments, and is gonna minimize the function we are giving to it and give us the fitted value. So we can initialize our vars or variables just to 0 as a starting point, because we have no idea what that is. And we're gonna use this least squared package. Our function would be the one we just defined. We have our variables dictionary, and the arguments would be x and data. Okay. And what I'm gonna do, I'm just gonna put it in a new object out. Okay. So I have a problem here, and let's see what the problem is. Because I didn't have that problem. Oh, okay. Here, vars is that. All right. So let's see what this out is giving us. Print out. So what it's going to give us is the best fit values for our parameters, which are A and B, the amplitude and the offset. And what it's telling us is that the best fit for A is this guy, and the best fit for B is this guy. Okay. Now, let's see what kind of chi-squared it's going to give us. So we can actually do the same thing we had here.
What is the 2?
So this is the number of variables in here. So what I'm going to do is just copy this guy here, but now my variables have, my vars dictionary has new values, these best fit values. So if I run this, I'm going to get a new chi-squared, and it's bad. I'm not sure why.
But you have to update your vars to be the one inside.
Exactly. So, okay, here's the deal. I was already in the LMFIT mode where every variable is updated automatically, and we already see that one of the advantages of LMFIT, like the variables are updated automatically. You don't have to change them each time. So, but we don't have that luxury here, so let's just do that. Vars would be this value for A and the other value for B. So I'm just defining them again, and now I get a chi-squared which is smaller than what we even had here. So we have a more optimized solution now. And actually what you can do, if we all of us are in the IPython notebook, let's just copy this, what we had here to save time. Let's just copy it here and then add the new fit to our plotting to see how good that is. So let's say I define a fitted curve, which is vars 0 times my x array squared I just defined, plus my vars 1. Okay. And then I'm going to add that to my plot just to see if it is really better than what we have. So I'm going to have my x array, and I'm going to have my fitted curve, and let's plot it with blue, for example. So here's the deal. It's obviously a better fit to what we had with hands. So we're already good. Okay. Now, so it's good. This is the built-in function in Python, and it does what we want. But we can work with LMFIT library because of many different reasons. First of all, here, if I change my parameters in my function, where is my function here? If I change my parameters or my model, I have to update everything each time I change things. The other thing is that this least squared method can give me error bars. It's using a specific method, and it can give me error bars, but it's not fully it's not always trustable. So you can have a more trustable error bars with this new library. You can have different methods for fitting, but here is just one specific method. With the LMFIT, you can have different methods and compare them. And in general, you have a better control over everything. And there are a lot of new functionalities that you can have. I can list them here if you want. I just listed these guys here, but I can copy them to our notebook so that we see them. Mark.
I think you changed the one on top.
I did. Markdown. Okay, so I'm just summarizing some of the advantages of LMFIT library here for a purpose. But now let's see how it works. The biggest advantage of this LMFIT for our purpose would be that you have a better control over these parameter values and dictionary. So let's work with LMFIT. What we're going to do is to load this minimize function from LMFIT, and the parameters library from LMFIT. Let's see if that works. Yeah, good. So let's make sure we have that. Are we good? Good. So let's define these params, which is this. It's an object for parameters. Just make sure it works. Okay. Now, the first thing is that we can dynamically add parameters to our library, to our dictionary. So the command would be params add. I can give a name to my parameter. I'm going to call it amplitude. And I can do a lot of things with it. I'm going to start with the first case where you can set the value of your amplitude function. I can add another one. Say, I'm going to call it offset. You can call it whatever you like. And I'm going to give a value of 0 to that again. Okay. Now let's just, if we are all okay, just copy paste our function and modify that. This is our get residual function. Let's just copy that. And put it here. Now we want to modify that. I can, so this A and B are internal variables for my function, but I can change the name just to be consistent. That's one thing. The other thing is that this vars dictionary can now be replaced with these params. So let's just do that. And just to be consistent, as I said, I'm gonna call this A as amp and this B as offset.
You should change bars as well.
Yes, that's the next step. So one of the ways to do that would be to say my params object has an element of amp, and I'm going to choose that as my amplitude. And I want to take the value of this object as my variable. And I'm going to do the same with the other one. I'm going to go with offset. And I'm going to use the value. Okay? And now my model would be just a modification, amplitude times x squared plus offset. So let's make sure this guy is okay. Yeah. Now I'm going to define the same out object, but the function I'm going to use is from LMFIT now. So I want to minimize. And the good thing is that it is similar to least squared function from Python itself, meaning that you give the function to it that you want to minimize. You give the variables you want to fit, and you give the arguments, which are x and theta. So it should give me a new object from LMFIT package. Now let's see what this out object has in it. Okay, we can do that, for example, with dir. So you can see that this object has a lot of associated variables to it. We can recognize some of them. You have a chi-squared associated variable. You have error bars. It's archaic information criterion, Bayesian information criterion. There are a lot of things here that should be useful, like params, which is probably the value of the parameters which are now fitted. So let's just check some of them. Let's look at the params. So it is the output for the params. It's not the best way of showing it. I'm going to show some other more interesting ways of showing it. But what it tells us is that the parameters I have in my fit are this amplitude, and the value of the fitted value would be this guy. And you should recognize that. It's similar to what we got from our least squared thing here, if you remember. So, okay. And it's giving us an error bar, and it's giving us the boundaries we put for this fit. The other one is this offset with this fit, this error, and this bound. So we didn't set the boundaries of the function, of the variable, so it's the default minus to plus infinity. But we can do that. If you like, you can actually look at, this is an object, so all these associated variables could be used. If you just want to look at the values, you can do that. It more or less gives the same output, but it's just a subclass of all the information we have in params. And of course, if you like to see more, you can use this dictionary associated thing.
But you can also actually use bars and out. The only issue is that here, because of row bars, it wouldn't work, but another way of getting just a bunch of attributes or something, it's like dir, but bars. It gives you all the...
Yeah. So you can say it again. DIR.
DIR, and there's also VARS. But try it, but it might not work because we've already used that variable.
We reassigned it. Yeah.
Yeah, I think so. It won't work. So, but basically, what it does is it just calls the derivative.
Yeah. Okay. Cool. But the point is that it should give us a lot of extra information if I could output it here. So you can already see what kind of information you could get. This information criteria, the chi-squared value, which should look familiar to you. This is what we got from ORFIT. The covariance between the variables of the model is one of the most important things, I assume. It's very important to see what kind of covariance you have. It gives you that the number of data is like you have 4 data points. 2 of them are free. We didn't fix any of them. That's another thing we could do. And these are my parameters. These are the residuals. So all kinds of interesting information you could have. The initial value was that here. Yeah, so far so good. Are we fine with that? Any confusion? Now, the next part would be to actually manipulating these variables. Let's say I want to fit, but I don't want to vary one of my variables, like this amplitude. I want to fix that. So the way to do that, if you wanted to traditionally do it, you have to just go and change the function. But now what you can do is just, okay, my prompt, the amp component, I don't want to vary it, so I put the vary to false. Okay? And what we should remember is that it is not going to vary if I fit it again. However, it's going to have the last value it had, which is this 1.6 something. It's not going to have the initial value anymore. It's going to have the current value. But the point is that you want to fit without that. So if I repeat the same guy, if I say my out now is minimized of my get residual, is practically the copy paste of the column up there. Terms args is x and data. Now it's a new fit where this parameter is fixed. Now if we look at, say, the same output, let's say I'm just going to copy paste the dictionary component. I suspect I'm going to get the same chi-squared Why is that? Because I already fitted my amplitude to the best fit value, and then the other parameter is also going to fit to the same value. So let's change it. And the way we're going to change it is that I'm going to also change the value of this guy to something bad, say 0. And I'm going to run that, and I'm going to run it again, the minimization. And now, if I look at the dictionary, I have a very bad chi-square, obviously, because I fitted my amp parameter. I fixed my amp parameter, and you can see that it's fixed now to the value of 0. So I'm going to get a bad chi-square.
So I didn't have to update my amp parameter to 0.
No, if you hadn't had this guy, it would fit, and it would have the previous value fixed.
No,
Right.
it has 0
Yeah, mine did the same thing.
without updating the amp value.
Are you sure?
I didn't look at that, but when I did it, it gave the 56 for chi-square without fixing it to 0.
So where could you go wrong? Because if it is the same, well, you can do it again. Let's change the value to true and run it again. See if you get. Let's see if you get that.
So change it to true.
And then output it and see if it is really fixed or varied.
Yeah, here, yeah, I think I have the same thing where if I fix the value gets set to 0 for some reason.
Yeah.
Okay, how about you fix it? It's surprising, but how about you fix it, but then put the value to something else?
Yeah, I'm going to try that.
Yeah.
It's strange. It didn't happen to me, but we can check that. Should be able to.
Okay, now that works now.
Yeah.
It automatically, I think if you say variable's false, it automatically sets it to 0.
Okay, let's do that now. I'm gonna do that. So if you're right, then it should be 0. Okay.
And then if you look at their value for
Okay. Good. I didn't know that. But it means that we have to. Okay. It means that we have to set the value after that. Okay. Now it's fixed to that. So how about a very quick exercise, like using the mean and max attributes and fit the minimum or maximum of the boundary of the parameter to some value you like, and then run it again. So let's say my amp is fixed now, but I want to change the boundaries of offset. It is -infinity to plus. Now I want to use these guys and change it to something else. And if you want to be mean, an interesting way would be to, how about this? Let the amplitude vary and also let the offset vary, but change the boundaries of offset to a value which is where the best fit is outside that boundary, and see what you get. Like it has to like hit one of the ends of the boundary. How about doing that? Is it clear? First of all, let's let the amplitude vary. Then let's use the mean and max attributes to set some limits for the offset range and see what we get. And then we can play with that. So let me know when you're fine with that. So what I did here was that I set the minimum and maximum value for this offset, and when I'm gonna run it, it's gonna show these values here. But I knew that the best fit value for this guy was 0.096. So I was mean, and I set a range where it's not, the best value is not there. Just to see, I haven't tried it, just to see how it's gonna behave. So let's try that. So I'm gonna do print output. Okay, let's see what happened. So I know that my amplitude parameter is varied, but it's not going to get the same value because the other guy is going to behave weird. And what you see is that the best fit now is not hitting the boundaries, but it chose another set of values to fit, and the chi-squared is very bad, but that's the basic one. So it's just that we don't have a proper boundary. But now let's just, I'm gonna be fair and give a different range to it and just run it again. And now you see that we got the old chi-squared as the minimum chi-squared, and the value is what we had before. Okay. So this is a good way of outputting things, but you might want to be cleaner. For doing that, there is another function in here, which we can import from LMFIT. Import. There is a thing called reportfit. Let's see. Okay, and you can actually see what this guy is doing. you want. It just prints a report for the fitted parameters. Okay. Now we can see if it's gonna give us a better output. So it's just nicer. It tells us that the function has been evaluated 12 times to get to the best fit. I have 4 data points, 2 variables. This is the chi-squared. This is the reduced chi-squared, very useful. And these are the best fit values and errors. Okay. All right. So whatever we've done so far is with the fiducial, like with the standard, with the default fitting method, which is this method here. But for whatever, it has an advantages and disadvantages, but it's one of the most tested methods, so it's good for our purpose. But you might want to try other cases. And LMFIT has some extra method for fitting. You can study them in detail, but a summary of them are here. So this least squared is like the default Python case, but you have all these other methods you could try. And all you need to do is to introduce to your fit, like here, that you want to change another, you want to use another method. So you can do that with the method comment, okay? And the name, which is here. So we can do that. How about doing that? How about fitting with, say, this truncated Newton method? So we're gonna use the same thing, but with this method and compare the results. Just to be able to compare, let's call it the result is equal to minimize, and the rest is the same. The only thing is that you have to add the method equal to PMC. So let's do that. So you're gonna fill out this. So the purpose would be to get the fit from that and compare the result output with the output. So if your function is funny, and you know some specific method is going to work better, then you have the choice here. For example, this default function is known to fit the local minima. Sometimes your function is funny, you're not going to get the global minima. In that case, you want to try other methods. We're good.
Yeah, they tried a lot more times.
But okay, but the point is that my function was extremely simple.
Yeah.
And I have a problem.
This isn't what happens in
Yeah,
science.
No, yeah, that's the problem.
It needs the arcs.
It needs what?
Arcs.
Oh yes. Arc is X and data. Yeah, unfortunately, it's much harder in real life. Okay, so you tried and you know it's getting the same answer, much more try and all that. Good. So as I said, there are many flexibilities this package is going to give you. I'm just going to give one other example, but if you're interested, you have to go to the website. The other is that sometimes you want to define an expression with which you introduce your variables. Now imagine I want to define another variable, amp squared, amp2, okay? But I want it to be, my model is so that it is dependent on the amp variable. So I want to kind of implement that. I know that my amp squared is dependent on my amp variable. So what I can do is that I just can dynamically add this variable, new one, and this is called amp2. But rather than giving it a value, I'm going to give it an expression. I choose, let's see, I hope the syntax is correct. I want it to be amp minus offset, for example, squared. It's just, I came up with it. Let's see if I have any error. No. However, so it's good, but it's just that I suddenly discovered this new parameter. I have to update my get residual function because it's not defined in there, right? If I already knew about it, I could put it in there. But let's just, for the sake of time, copy paste the get residual thing and add this new one. And now that we're on it, let's just describe another way of introducing these parameters. So I'm gonna comment them out. And let's define this way. I say, okay, power valves is just a new variable, is my prompt, but I know that this guy has an attribute values big. Okay. Now, all the values of all the parameters in this params object are now going to this power valves. Okay, and then I can say, okay, amp is my power valves amp. Not that it's an easier way. I'm just want to show that you can do it in many different ways because these are all attributes. So offset would be this power valves offset, and now I'm gonna define my new thing. Amp squared is power valves amp squared. Power valves squared. Okay, and I'm gonna actually put it here as something of a second order correction, we can call it, as an x to the fourth element. Okay. Now let's minimize it again, this new function, and see what we get. So I call it result2, and I'm gonna be lazy and just, it's not the best way, it's not nice, but hopefully you're gonna be fine with it. So what I did, I added this new parameter and I introduced it here, and now I want to fit it. Are we fine with that? So how about we use this report fit with my new object result 2. And the point is that this result 2 itself is an object. I could print the whole thing, or I could just say I want the params attribute of that. It's just that, again, we can look at a specific thing. Now, here's the deal. We have a new fit, of course, because the function changed. But this amped squared is not an expression, which is dependent on the other guys. So you can have complicated models where these things are all dependent to each other. And the point is that, one thing I forgot, if the correlation between these parameters are output only if they are larger than 0.1. And what it says is that these two are very correlated now, extremely correlated, just because I defined something which connects them to each other. So obviously they are very correlated. Okay. But then that's a way to define new expressions. I could define any expression I wanted. It's just that for simplicity, I defined it like that. Again, it's just an example of what kind of, and there is a complete dictionary of these expressions for this LMFIT that you could use. It gives you a lot of flexibility. Okay.
Is the library simplified? You showed some plots earlier. Is it simplified by the plotting process, or is it as easy as when you're using it?
So plotting had nothing to do with that. With the library, I just plotted that. I'm not sure if they have. What this thing is not showing. I think they have curve fitting, but they don't have that much of plotting capabilities. Plotting would be. It's more about fitting than visualizing and plotting. Yeah.
I was curious about, like, because it reports error bars.
Yeah.
It would be nice to be able to plot those, like, the bounds of the model.
Exactly. Not well. For sure. Okay, that's good. Maybe it does that. Now that you're saying, but I haven't checked. Yeah. In the worst case, you have to extract them. I think. Okay. Here's the deal. I think you can do that. Params stdr standard error of some kind. Let's see if std error. Let's see if it. No. Let's do that. Let's do params amp std error. Oh, okay, but it doesn't print it. Interesting. Std error. Oh, okay, because it should be in the result 2 object. So you can directly output these values and then put in your plotting thing. So that should be fine. I guess that's why they haven't invested in plotting that much, because you can just use the normal matplotlib.
Do one thing and do it well.
Exactly. Sure. So my purpose was just to show that what kind of things you could do with this, but it's so big that it needs you to really look into it. So I guess I just stop here, unless you have questions. If you've been involved with fitting and like minimizing, then you would know what a headache it could be. If you happen to want to do it in Python for whatever reason, for example, then you would know that this could be very useful.
So I have a question. So for me, it's that I probably have some sort of logarithmic function that describes like a dose response.
Yeah.
And some of my components will have a good dose response curve. Some of them will have a bad one. So I can use this package to try to fit all of those things and then just get a chi-squared from that.
Yes. Yeah, exactly. Yeah, you have a lot of freedom in defining whatever the function is. Okay. Good. Thanks. Now. Thank you. So I have to push this button and read
It's
that.
not project.